So, good morning, students. Yes. So, what we have discussed in the last class, anyone? Hmm? Can you tell me? Right? So, we are in the last part of this topic. Okay? So, we are in the last part of this particular topic. So, what we have discussed? Hmm? Okay, shielding effect and nuclear force N plus L rule. So very good. So first thing we have discussed about Aufbau diagram. Right? So we have discussed about Aufbau diagram. So why this Aufbau diagram is required, or what Aufbau diagram talks about? It talks about distribution of electron with respect to lower energy to higher energy, right? So that's where Aufbau diagram talks about. So what it tells? It talks about distribution of electrons from lower energy to higher energy. Yes. So many of you have written that one, Aufbau principle or Aufbau diagram. So that's what we have discussed in the last class. Then, as people have written, then we have discussed about degenerate orbitals, right? Then we have discussed about degenerate orbitals. So, what do you mean by degenerate orbitals? So, these are the one which will be having, or these are the group of orbitals which will be having same energy. Okay? So, all of you have written, it's proper. So, Aufbau principle, degenerate orbitals, then shielding effect. So these are some of the concepts we have discussed. Now when it comes to hydrogen, right? So if I take the degenerate orbitals 2s, 2p, or 3s, 3p, 3d, right? Like that it will goes on. Okay? So whichever orbital belongs to any one energy level, they can be considered as degenerate orbitals with respect to hydrogen atom, where only one electron will be there. It can be hydrogen atom or hydrogen-like species, where only one electrons will be there. But for rest of the element, where number of electrons will be more than 1. So in that case, that's where there will be difference. 2s will be of lower energy compared to 2p, which will be of lower energy compared to 3s, which will be lower energy compared to 3p. Then comes the 4s, then comes the 3d, right? So that's where we have to follow Aufbau diagram when it comes to these things. Hagadre, when it comes to rest of the element, which are those degenerate orbitals? Those can be 2px, 2py, 2pz, or 3px, 3py, and 3pz. They can be degenerate orbitals. So 2s will not be equal to 2p in case of the elements other than the hydrogen and hydrogen-like species. Fine? All of you have understood? So this is what we have discussed. Then, why in case of the elements which are having more than one electron? So that's where we have discussed about shielding effect. That's where we have discussed about the shielding effect. So what shielding effect talks about? What do you mean by shielding effect? So shielding effect is nothing but, yes Pooja, you are right, electron repulsion, then shielding effect, then shape of the orbitals. That's why in case of the element which are having more than one electron, they differ from hydrogen. So what are those reasons? One is shape of the orbitals, next one is with respect to electron repulsion, then shielding effect. Okay, so what do you mean by shielding effect? It is the lesser amount of nuclear force felt by the outer electron due to the intervention of the or interference of the inner shell electrons, right? So that's where we have the shielding effect. All of you have understood? So that is related to nuclear force, amount of nuclear force acting on the outer shell electrons, which will get reduced due to the interference by the inner shell electrons. All of you have understood? That's where we have the shielding effect. Okay? Any doubts? Then we were talking about N plus L rule. Then we were talking about N plus L rule. So according to this rule, it tells that for a given electron, which is having highest N plus L value, they will be considered with higher energy. Okay? Any electron with higher N plus L value will be of higher energy. That's where we have the one particular statement. So any electron which is having higher N plus L value, then that electron will be of higher energy. Okay, that's where we have N plus L rule. But there is a point, like yesterday we have seen. So when it comes to 4s and 3p, like that we can take many examples. Okay, so 4s and 3p, if we consider, we have seen that N plus L value for 4s, N plus L value for 4s will be, right? So what is N value? N is equal to 4. What is L value? L is equal to 0, because S subshell will have the 0 value. Okay? So that's 4. That's why N plus L value for 4s is N plus L value for 4s is 4. Now in that case, when it comes to N plus L value for 3p, right? So that's where N is equal to 3 and L is equal to 1, because we have P subshell. So therefore N plus L is equal to once again 4. Hagadre, which will be of higher energy among these two? Among 3p and 4s, which will be of higher energy? So naturally we should consider which are those having higher N value, that will be of higher energy. All of you have understood? So what I mean to tell here is, listen to me carefully. According to first statement, any electron with higher N plus L value will be of higher energy. Done. That is fine. But if they are having equal values of N plus N, then which will be considered as of higher energy? Then we have to think that electron with higher N value will be of higher energy. So this particular statement applicable when we have N plus L of equal value. So naturally 4s, not 4p, it should be 4s will be of higher energy, because N value is higher in case of 4s. All of you have understood? So that's why we have N plus L value. Now yesterday Rohan was asking, Rohan or someone, I don't know, I forgot, with regard to 4s and 3d. Why 4s will get filled up before 3d? That was the question. You can apply the N plus L rule here. Okay? So you can apply the N plus L rule. According to Bohr diagram, what we had seen, 4s will get filled up first, Then comes the 3D. And then the question was, how come it's possible? So that's where n plus L rule can be applicable. So for 4s, n plus L value is equal to 4. And for 3D, what is the L value for D? It will be 2. So naturally it will become 3 plus 2, that is 5. So among 3D and 4s, which is having higher value? So 3D is having higher n plus L value. Therefore, 3D will be considered as higher energy compared to 4s. Don't get confused. So since yesterday in F-board diagram, when I draw the F-board diagram, there was a question. Sir, how come 4s will be getting filled up before 3D? So that's where we have got the answer. That's where based on n plus L rule, we can tell that 3D is having higher n plus L value. So therefore, 3D should be of higher energy compared to 4s. Okay? So all of you will agree with me? So that's where we have got the answer. Any doubts? Any doubts up to here? So this n plus L rule, bit important. Okay, any doubts up to here? So that's where we have the F-board diagram. Okay, that's where we have the F-board diagram, which can be based on n plus L rule only. Okay. Shall I move to the next one then? Okay, fine. So we will move to the next one. That is Pauli exclusive principle or Pauli's exclusion principle. Exclusion principle. Okay. Now, many students they will write Pauli, not Pauli, not P-O-L-I. It is P-A-U-L-I. Pauli. Pauli exclusion principle. Okay. Now, exclusive means compulsory. Okay. So, what is that compulsion here? That compulsion here is no two electrons. No two electrons can have all the 4 quantum numbers. All the 4, because we have total 4, right? So all the 4 quantum numbers same. All the 4 quantum numbers same. It's not at all possible. That's what Pauli's exclusion principle tells. So what is that? No two electrons. No two electrons can have all the 4 quantum numbers of same value. So that's what it tells. So no two electrons can have all the 4 quantum numbers same. They have to differ with respect to any one of the quantum number, or to be more specific, 2 electrons can have same n value, they can have same L value, they can have same ml value, but they differs in that at least spin quantum numbers. At least differs in spin quantum number. They can be having same n value, they can be having same L value, they can be having same ml value, but they have to differ at least in spin quantum number value. So in that case, how come they can have same n, L and ml value? See, for example, I have a electron present in 3p. In an atom, I have electrons which are present in 3p subshell of an atom. Now, what is the n value over here for 3p? What is the n value? Anyone? What is the n value for 3p? Any one of you can write n value for 3p? Yeah, very good. So n value is equal to 3. That means all those electrons which are present in 3p, they will be having principal quantum number as 3. So what about L value? Yes, all of you right. What? Okay, Rakesh, why 4? I am talking about N value, not N plus L or nothing like that. So what should be L value? For that electrons which are present in 3p, what will be L value? L value is equal to 1. Yes, L value should be equal to 1 because we are dealing with P subshell and L value should be equals to 1. So that means if I consider there are total 6 electrons, we will imagine there are total 6 electrons. 1, 2, 3, 4, 5, 6. So total 6 electrons are there. So in that case, we will go with any one of these 2 electrons we will consider. First one only we will consider. Okay. So these 2 electrons, they have the N value is equal to 3. So these 2 electrons, they have the L value is equal to 1. What about ML value? What about ML value for these 2 electrons? Whether it will be same or they will be different. I am only talking about this particular 2 electrons, not these 2. This one in 2 electron I am talking about. So N value is equal to 3, L value is equal to 1. Whether ML value will be same or they different, you should tell me. You can just type it as same or different, DIFF, that is enough. So whether they should be same or different. Okay, according to Stephen, it should be different. All of you will agree with that? No, that's fine. 3 is fine. So ML value, total value be 3. But we have those 3 values as -1, 0, +1. Okay. So some of you are writing same. Shashank is writing same. But rest of you are telling 3. ML value 3 is not the value. Please remember. 3 is the total number of values. Which are those 3 values? Those 3 values are -1, 0, +1. So in that case, they should be same. Because I will consider this one as -1, this one as 0, and this one as +1. So in that case, both the electrons will have -1 value only. They will be having -1 value only. All of you have understood? So that's where I have 2 electrons which are having same N, L and ML value. So that is 3, 1 and -1, both the electron. Because both the electron belongs to one orbital only, same orbital. So therefore, they should have all the 3 values same. But what about spin quantum number? That's where they differs. If I talk about this electron, it will have +½ value. If I consider this one, it will have -½ value. So that's where they will be differs in their spin quantum number. They cannot be same. They cannot be same. That's what Pauli's exclusion principle talks about. No 2 electron can have all the 4 quantum numbers same. Okay? They can have 3 values same, 3 quantum number. That is principal, azimuthal, magnetic quantum number. But they have to differ in their spin quantum number at least. That means all the 4 quantum numbers, they are not same for these 2 electrons. Okay, for these 2 electrons. All of you will agree? Okay. If I consider this electron with this electron, they differ even in their ML value also. They differ in their ML value. Okay. So that's what Pauli's exclusion principle talks about. Any doubts? Shubhangi, it cannot be different. It will be same. Rohan, Harshita. Okay. So all of you had written different value. It will be different value until N, L and ML, they will be same. But yes, spin quantum numbers will be different. Yes. All of you have understood? Any doubt? Okay. Shall I give another one? Okay. Okay. In that case, you should tell me quantum number values with respect to principal quantum number, magnetic quantum numbers, and azimuthal quantum number. For electrons which are present in the same orbital, calculate the or mention the, anything is fine, calculate the N, L, Ml and spin quantum number for two electrons of different orbitals in 3D. Okay, in 3D, only two electrons you can mention. Okay, so how to find out? So first thing, if I want to give the answer, so now since they are talking about two electrons of 3D, right? So what will be the N value? N value will be 3. Those electrons will have N value as 3. What about L value? L value will be equal to 2 because we are dealing with the D subshell. They will be having same N and L value. What about ML value? Because when I am talking about D subshell, how many orbitals we have? Total 5 orbitals we have, right? So that can be dxy, dyz, dxz, dx square minus y square and dz square, right? Now we will imagine these orbitals are completely filled. So naturally, if I want to talk about this electron and this electron, see the arrow, okay, this electron and this electron. So what will be the ML value? No, not only -2, okay. So if I consider -2, -1, 0, +1, +2, that means one belongs to -2, another one belongs to +2. So it will be -2 and +2. Okay. Now what will be spin quantum number value? Whether it will be same or it will be different. Spin quantum number value, whether it will be same or it will be different. Anyone? Whether it has to be same or it has to be different. Spin quantum number I am talking about. So whether they will be same value or it will be different value. No, Rakesh and Sanya, they cannot be different, they are same. See here, spin up, I have shown the arrow. So spin up and spin up, both are +half. Both are having +half value only. Both will be having +half value only because both are spin up, upper arrow. Okay, that's why I have shown the arrow also there, which two electron I am talking about. That's what I have mentioned with the arrow. So it should be same. But whether all the 4 quantum numbers are same? No. In this case, the difference in their magnetic quantum number. That's what Pauli's exclusion principle tells. No electron can have all the 4 quantum numbers of same value. Okay? So that's where we have the Pauli's exclusion principle. Okay? Any doubts in this? Okay? If you have any doubts, you can ask. And you can expect the question like to find the quantum numbers for an electron present in 4s, 3p, like that. You can expect the question. Then you have to mention what is the n value, what is the L value, and all you can mention. Sir, in the last box, why we take upper arrow? Because I have shown that simply I had asked that question. Those two electrons you consider, that's what I told. Okay? So that's why we have to consider upper arrow, because purposefully I have ticked those two electrons. That's all, nothing else. Sanya, that's what. I took spin up electrons. It's my wish. Nothing like that. Purposefully. It's not compulsory. I have to take only spin up only. No. Fine. So if I take one spin up, one spin down, then it will be plus half, minus half. Since I have considered only spin up, then it will be plus half, plus half. That's all. It's not compulsory. But here I have made it as compulsory by showing the electron. That's all. Okay. So Ullas and Sanya. Okay, Sanya. So whether I am clear? So we will come to last part. Okay, we will come to last part of the topic. That is Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity. Okay. So now in this case it tells that when we are dealing with the maximum electrons in a particular orbital, so it is applicable for those orbitals or for those subshells which are having more than one orbital. So that means Hund's rule of maximum multiplicity is not applicable for S subshell. Is not applicable for S subshell because only one orbital is there. Okay? But it is applicable for rest of the subshell. That means P, D and F. It's applicable for rest of the subshell which are having more than one orbital. But not applicable for S subshell. Why? S subshell is having only one orbital. Okay? So what is that Hund's rule of maximum multiplicity talks about? What it tells? It tells that with respect to subshells containing more than one orbital, electrons will not be paired. Okay? Electrons will not be paired. Until all the orbitals receives the at least one electron. All the orbital receives the at least one electron. So that's what Hund's rule of maximum multiplicity talks about. So what it does with respect to subshells containing more than one orbital. Okay? Electrons will not be paired until all the orbitals receives the at least one electron. So what I mean to tell you is, okay, so here I am even discuss about the electronic configuration also, fine. So what I mean to tell you is, say for example, I have 4 electrons. I have the 4 electrons. Now I have p subshell. I have what? P subshell. So these 4 electrons I have to distribute them into p subshell. Now p subshell is having how many orbital? It is having 3 orbital, 3 boxes, right? So first I have to make entry of one electron in these boxes. Okay, so then only I can make entry of fourth electron. That means there is a pairing of electrons. Or if I want to have 3 electrons, I have to distribute that one into p subshell. So once again, I have got p subshell. How many orbital? 3 orbital. That means 3 boxes. Now I cannot write 1, 2, 3. So this is absolutely wrong. This is not correct one. This is wrong. Actually, according to Hund's rule of maximum multiplicity, it should be like this. This is correct. It should be like this. Got my point? So until unless each orbital will have 1 electron, I should not make the pairing of electrons. No. Fine? But it is applicable only to those subshells which is having more than 1 orbital. When it comes to a subshell, only single orbital is there. If I have 2 electrons, I have to fill that S subshell completely. Okay? So that's where I have the Hund's rule of maximum multiplicity. Any doubts? Any doubts? So with respect to subshells containing more than 1 orbital, electrons will not be paired until the orbitals receives all the orbitals receives the at least 1 electron. Okay? So that's where Hund's rule of maximum multiplicity talks about. Fine? So we will move to next one then. So we are coming to the last part, that is writing the electronic configuration. Writing the electronic configuration. Okay? Now, as I told in the last class only, to write the electronic configuration, what we require? Anyone? Any one of you? To write the electronic configuration, what we require? That's where we have the electronic configuration. For 1 mark question you can expect. Okay? So electronic configuration. So to write the electronic configuration of any element, first and foremost thing we should know is atomic number. What is the atomic number of that particular element? Because with respect to neutral atom, it can be number of electrons. It can be number of electrons. That's why in a neutral atom I will mention. Okay? So I should know what is the number of electron. To know the number of electron, I should know what is the atomic number of that particular element. Then another very important point I should know here is Aufbau diagram. Aufbau diagram. I should know Aufbau diagram. Even you can write it on one corner of your answer script. No one will ask the question. You have that freedom. You can write it on one side of your answer script, Aufbau diagram, to avoid the mistakes. All of you have understood? And if you know these two information, then easily you can write the electronic configuration for anything or any element. Fine? So in that case, first I will write the Aufbau diagram. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6s, 6p, 6d, 6f. Okay, this much is enough. For a hydrogen, yes, they are of equal energy. They are of equal energy. They are of equal energy. But for which one? For hydrogen. But when it comes to Aufbau diagram, no need to write it as an answer. This is for your information, to avoid the mistake. you can write it on one corner of the page. Okay, so that you can follow the Aufbau principle or Aufbau diagram. No one will ask you to draw the Aufbau diagram. No, they will not ask. Fine? When it comes to distribution of electrons, so that's how electrons will be distributed. Right? So that's how the electrons are going to get distributed. So that's where I can see. So 3p, 4s, after 4s, 3d, after 5s, 4d, after 6s, 4f, it will come, and 5d will come. So that's what we can see here, according to Aufbau diagram. Right? So now, if they ask, write the electronic configuration for, write the electronic configuration for fluorine. Write the electronic configuration for fluorine. Right? Now, symbol is, all of us we know, F. Now, first we should know what is the atomic number for fluorine. So, fluorine atomic number is 9. Fluorine atomic number is 9. So, we have to distribute these 9 electrons. We have to distribute these 9 electrons. Now, when it comes to fluorine, so that type of electronic configuration is applicable only for 10th standard Rohan. Okay? It's not for PUC. In PUC you have to give detailed information. If you write 2, 7 and all, they will not give the marks. Okay? So, when it comes to fluorine, I will write the electronic configuration as 1s2, because S subshell is having only one orbital, it will be completely filled, that is 1s2. Now among 9, 2 got over, rest 7 is left over, in that 2s2. Another 2 electron will enter into next energy level, that is 2s2. Right? Then after 2s2 it is 2p. How many electrons are left over? 5 electrons. So that's where we have 1s2, 2s2, 2p5. Now it is absolutely correct. Yes. And please remember, anyway, now you are typing it in a text, this one. When you are writing it on the paper, 2, 2 and 5, they should be always superscript. Fine. So that's where we have the fluorine. Now, another way of writing the electronic configuration is that, which we will understand once we go with the periodic classification of elements. That is by using the inert gas. We can write the electronic configuration. But anyway, that one I will teach you when we will move to the next chapter. That is periodic classification of element. But for time being, you can remember, this is how the electronic configuration can be written. Now I can tell that when it comes to fluorine, in the outermost energy level, it is having 7 electrons. Why I am considering only those 2 as outermost energy level? Because they are with higher n value. Okay? So therefore, it is having in its outermost shell. How many electrons? 7 electrons. So therefore, whichever electrons they are present in outermost shell, they will be considered as valence electron. Naturally, in case of the fluorine, it will be 7. So what is that total number of valence electron? It will be 7. All of you have understood? So that's what electronic configuration will give the information. What is the total number of electrons present in each energy level? How these 9 electrons are distributed? So based on the electronic configuration, we can tell that 2 electrons are present in energy level 1 in S subshell, 2 electrons are present in energy level 2 in its S subshell, and another 5 electrons are present in P subshell of this particular energy level 2. That's how the information will be given by electronic configuration. It talks about how electrons are distributed in an atom, in their energy levels. Fine, all of you have understood. Now, if I want to go with box type representation of Bohr principle, this is more than enough for electronic configuration. If I want to go with Hund's rule of maximum multiplicity, then I can tell that 1s2, then 2s2, this is 1s2, this is 2s2, then we have 2p5, then we have 2p5, observe it carefully, 1, 2, 3, 4, 5, that's how it will be shown, based on the Hund's rule of maximum multiplicity, right? So first what we did, first one electron we entered, then another extra electron we entered here so that it can pair up, another one electron we entered so that it can pair up. Now no more electrons are left over, so it will be empty. Only one electron will be there in the last orbital of 2p. Got my point? All of you have understood? Any doubts in this? That's how electronic configuration can be written. Can any one of you write the electronic configuration for argon? Write the electronic configuration for argon with atomic number 80. Argon with atomic number 80. Write the electronic configuration for argon with atomic number 80. Argon symbol is Ar. Atomic number 18 I told. Right? So for that electronic configuration can be 1s2, 2s2, 2p6. So total how many electrons are over? 10 electrons are over. 6 plus 2, 8 plus 2, 10. So 10 electrons are over. As there is only one electron in last orbit, it's very reactive. Yes, due to that it's very reactive. That one we are going to discuss in periodic classification. Okay, yes, you are right. So 1s2, 2s2, 2p6. Still how many electrons we have to write? Rest 8 electrons we have to write. Some of you have written absolutely correct. So that is 3s2, 3p6. So 6 plus 2, 8. 8 plus 6, how much it will be? 14 and 4. Right? 80. So total 80. Right? Now if I want to show only outer electrons, then these are the outer electrons because they are present with highest principal quantum number. So they are the valence electron. So what is that total valence electron in argon? It is 8. Total valence electron in argon is 8. So now that's where I have S subshell, that is 3s2. Only this one I am writing. Then 3p6. So 1, 2, 3, 4, 5, 6. So what it means? It shows that 3p subshell is also completely filled with electron. There is no place for any electron. It is completely occupied. So that's where argon is stable. Rohan, that's where answer for your question. You told about fluorine, right? Yes, due to that fluorine is reactive, and due to that argon is very less reactive because it is having completely filled outermost orbital. Got my point? So that's why it can be considered as stable electronic configuration. We can consider this one as stable electronic configuration. Why we are calling it as stable electronic configuration? Because they are having completely filled outermost orbital. So that's why it is an example for stable electronic configuration. All of you have understood? Okay. So in that case, can you write it for nitrogen? Can you write it for nitrogen? So nitrogen is having atomic number of 7. Nitrogen is having atomic number of 7. Yes, argon is highly stable. Yes. Yes, you are right. Yeah, Sanya, I will tell. So when it comes to organ, you can see here clearly that this will be considered as outermost electron because they are having higher n value, that is 3. Rest of them they are lesser than 3, right? So if I observe the outermost this one, anyway inner one has to be filled. Then only electron will move to the next energy level. Until this level will not get filled up, it will not move to next energy level. So that's why we are focusing on outermost orbital. So if I see that one, maximum electron which can be accommodated by a subshell is 2 because only one orbital. Maximum electron accommodated by p subshell is 6 because 3 orbital. So that means all the orbitals are filled up. No spaces are left over. So therefore argon is a stable element, very less reactive element, and therefore this electronic configuration can be considered as stable electronic configuration, not the previous one. For fluorine, it's not considered as a stable electronic configuration. All of you have understood? Yeah, all of you have written the electronic configuration for nitrogen already. Very good. So 1s2, 2s2, 2p3, right? So 3 plus 2, 5, 5 plus 2, 7. That's why we have the 7 electron, right? Now, if I want to talk about only outermost electron, then I have, 2s2, I have written it as 2p. So it should be 2s2. Okay? So now, only one box for 2s2. And when it comes to 2p3, that's where 1, 2, 3, it got over. Okay? Now what I can observe, when it comes to p subshell, how many maximum electron can accommodate? Any one of you? Yes, valence electron is 5, no doubt. So total valence electron is 5, no doubt. Absolutely correct. So now can you tell me what is the total number of electron? Yes, Chidwan, p subshell can accommodate total 6 electron. But how much it is here? How much it is here? 3. That is half. Half of 6. Stephen, observe it carefully. Okay? So here it is 3. Half of the 6. So therefore, we have a condition where we have half filled p subshell in the outermost shell. We have half filled p subshell in the outermost shell. So therefore, observe it carefully. Therefore, in an atom, in its outermost shell, if they are having half filled orbital, not s, I am not talking about s, I am talking about p, d and f. Okay? So any of these 3 subshell in the outermost orbital or shell, if they have half filled electronic configuration, then also it will be considered as stable electronic configuration. Then also it is considered as stable electronic configuration. Okay? So we have 2 types of stable electronic configuration. So one is where it is getting completely filled, and another one is where it is half filled. So whatever half filled concept I am telling, it is applicable for P, D, F. Majorly it is applicable for P, D, F, not for the S subshell. Don't consider S1, whichever element is having, they are stable. No. It is applicable only for P, D and F. So that means any electron which are having 5 electrons in its D subshell and 7 electrons in its F subshell and 3 electrons in its P subshell in the outermost shell. In the outermost shell. That means all of them, they are having stable electronic configuration. Right? So 3 electron in its P subshell, 5 electron in its D subshell, 7 electron in its F subshell. Because D subshell can accommodate how many maximum? 10 maximum. Half of 10 is 5. So F subshell can accommodate how many maximum electron? 14, because it is having 7 orbital. So in that case, half of 14 is 7. So therefore, any element in its outermost shell, if they are having this condition, then it is considered as stable electronic configuration. All of you have understood? Half filled or completely filled? All of you have understood? Any doubt in this regard? So what you can do is, you can practice with the atomic number, with different atomic number from your check sheet. Okay, so from your check sheet, and once again during the periodic classification topic, once again we are going to practice some more electronic configuration. Okay, don't worry. But any doubts in this? Okay, any doubts? So in that case, shall I start? I will give an introduction about periodic classification. Okay. Oh, Shubhangi, no sir, in the sense, no need to go for this one. Okay, no doubt. Okay, done. Okay, fine. So in that case, when it comes to periodic classification, because in the next class, we are going to, okay, Rohan, yes, I will start it on Monday. Okay, done. So with respect to periodic classification, we have to discuss. Okay, sir, CET JE questions related to this chapter. Yes, we will see. First, we will finish it off one by one chapter. Already we are lagging behind. Time is less. Okay. Even first chapter, basic concepts of chemistry, whether it has been done, means not by me, at least by other faculties. CET JE questions with respect to basic concepts of chemistry, first chapter. CET JE questions they have discussed. Okay. So in that case, I think it will be done. Don't worry. Fine. So we will start with periodic classification. You just practice whatever chapter we have finished. It will be done. Don't worry. Yeah. Even I think it will be done. Don't worry. Pooja, what is that? No, sir. It's done or it's not done? Chidwan is telling it's done. Even I think it's done. Okay, for batch 2 it is done. Okay, fine. So we will see. I will discuss with that one. So don't worry, it will be done. Any doubts with respect to atomic structure or structure of atom? A very large chapter. In that case, batch 3 also not done. Yeah, yes, Rakesh. That's what she was telling. Sanya was telling. Okay, done. So I will discuss with the teachers, with madam, and I will let you know. Okay. So no need to worry about CET, JE questions and all. Definitely it will be done. Okay. So thank you very much. Take care and practice from your check sheet related to structure of atom. More practice. Okay. So thank you. Take care. Okay, thank you. Yes, thank you.